So we took the two extreme cases to start with. One, the case of t equals 0, where v is 0. And one, the case where I inject a long, infinite long current pulse, and then I get the steady state case when t equals infinity, v equals IR. But let's see at other locations, because we want to really see the whole development of voltage. And I want to take a very specific case where t equals RC. So you can see that the units here, I multiplied by R, the units are V, voltage. And so this should be unitless. This means that R multiplied by C should be in units of time. And I take a very particular case where t, the time of the injection, is exactly R multiplied by C. By the way, we'll mention this a lot. This RC value is many times called tau, or sometimes tau membrane, tau m. So tau symbolizes the value of RC. It's in units of time. This is in units of seconds, yes? In units of seconds. So let's see what happens to voltage, to the voltage, when you inject T exactly equal RC. So what do I really talk about? I'm looking at the case where I inject the current I. I get, as we saw before, voltage V. This is T. And I'm looking at a particular time here, T equal RC, or tau membrane. Okay? So I inject the current this long, and I'm looking for the value of V, the value of V here, after one time constant. So what will be the V at T equal tau? Okay? We can see that when T equal RC, this is becoming RC divided by RC becomes -1. So we see here 1 minus e to the power of -1. So here we see the following. V at T equal tau is equal IR multiply by 1 minus e to the -1. And this part is 0.63. So this means that after T equal tau, I get the voltage gets into 63% of the maximal voltage that it reaches. So here I get, at this location, 63% of V infinity, which is my IR. This is V infinity. So that's something interesting. I wait for a particular period of time, tau m. I inject the current for this time, and I know from the equation that the voltage will develop to the value of 63% of the maximal that it can get. The maximal here, again, this V infinity is IR, this maximal point. So that's when the voltage is being built, and you can see that if I would inject another time constant, and another time constant, and another time constant, the voltage will grow and grow and grow, as described here. It will grow and grow and grow exponentially, like 1 minus exponent, and eventually it will get, if I wait enough time, I will get close asymptotically, I will get asymptotically close to the maximal value, which is IR. Okay? You can see, you can use the same equation, exactly the same equation, you can use and ask yourself, how does the voltage decays when I complete the current? So I stop the current here, and I ask myself, how will the voltage look? How will the attenuation look at the end of the voltage? I already told you that it decays and goes back to its zero value. And one can show from the same equation that the attenuation of voltage by the end of the injection is also exponential, but in this case not 1 minus exponent, but just pure exponent. So let's say that we started with some value here. Let's call it V0 here. Oh, sorry, let's call it V star, which will be the voltage when I stop the current, and I'm looking at the voltage attenuation here. I can tell you that this curve, this attenuation, is equal. Sorry. That the voltage after I stop the current will look like the initial voltage here, attenuated like the same exponent e to the power of tau m. That means that if I wait 1 tau here, I will get attenuation to 63% from the start. I started, let's say, with 10. I will attenuate it by 63%. I attenuated by 63%, and I will be left with 37%. So I will get here, after 1 time constant, I will get 0.37 of V star. So both the growth of voltage during current is 1 minus exponent, but governed by the same exponent here, which we call tau m. Both the growth of the voltage and the attenuation of the voltage after I stop the injection are governed by the same exponent, by the same tau, but the growth is 1 minus exponent, and the attenuation is just the initial value multiplied by exponent. And so both the growth and the decay are mirror image of one each other. So if I take this point and put it here and flip it, the attenuation is exactly like the buildup. It is governed by single exponent, by tau m, and this is called the membrane time constant. The membrane time constant. It's a very important parameter which we should discuss in a second. The membrane time constant, you really should remember this. It's a very, very important parameter for understanding nerve cells. Tau m, the membrane time constant. So just to complete this part, okay, we started with an RC circuit that describes the RC circuit that describes for a first approximation a spherical, isopotential, passive structure, and I'm using the word passive now for the first time, saying that every parameter that I'm using, both R, C, current, everything is linear and fixed. Doesn't change during the injection. It's fixed values. This is in ohms, this is in farads, this is in ampere, and this is fixed. So it's a passive system. And this RC circuit is a good representation, as an initial representation of a cell. And if this would have been the case, then you can see that when you inject current I, you have, during the injection, the voltage develops like 1 minus exponent. And after you finish injecting, you stop injecting the current, the voltage decays like exponent. And the controlling parameter, the important parameter that controls the time scale, how fast the voltage develops and how fast the voltage attenuates after the injection, is governed by this time constant. That's why it's so important, the membrane time constant. For example, if the membrane time constant is long, this means that it will take long time for the voltage to attenuate, long time. If the time constant is short, it will be much shorter to attenuate or to build up. So the time constant controls how fast the membrane voltage responds to current. I inject a very fast current step, and it takes time for the voltage to respond. And after I stop the current, it takes time for the voltage to go back to its initiation value, which is 0. It takes it time. It has a memory. There is a memory for the membrane, if you want to call it this way, a memory for the previous current. It takes time to get rid, for the capacitor to discharge, to get rid of the current that I injected. It takes time, and this time is governed by tau membrane. It's a very important parameter because it tells you something about the memory, the electrical memory of the cell. Short time constant means that the cell gets rid, develops fast voltage, and gets rid of the voltage. And slow time constant means that it takes very long to get rid of this voltage. Another important parameter is R. So you can see that this equation is governed both by R, which appears both here and here, and also by C, which when multiplied by R is tau. This R, which is sometimes called R input also, the input resistance of the cell. Input resistance. Input resistance is another important parameter. So this R, or R input, is an important parameter because, as you saw before, it determines the maximal value of the voltage you can reach. So I multiplied by R is the maximal voltage that your voltage can reach. And so if R is very big, if the resistance of the membrane is very big, you get very high, very large voltage. If R is very small, you will get IR, which is small. You will get less voltage. So this R is important parameter to tell you how much voltage will I get, how much depolarization will I get when I have a given I. And RC tells you how fast the voltage develops and how fast the voltage attenuates following the current injection. So both R input and the time constant are the two critical parameters. Both the R input and the time constant are the critical parameters for understanding passive RC circuit, which is the first passive linear approximation for biological membranes, and in particular neuronal membrane.